Hi, this is Mingxiang. I'm very glad to be here to introduce our work, Predicting Geographic Information with Cellular Automata. Our paper presents a novel neural network design using Cellular Automata to predict geographic information. Cellular automata is a widely used modeling theory, taking Conway's game of life as an example. It is defined on a two-dimensional finite grid, where each square on the grid is a cell. It has two possible states, 0 and 1, or in other words, dead cells and live cells. A cell has its own neighborhood. The rule is actually quite simple, that each cell would evolve in discrete time dimensions according to certain local rules. Taking this cell as an example, it has 3 live neighbors in step 1, so that in the next step, it becomes a live cell. Cellular automatons use vectors instead of numbers to represent cell states, so that each cell can take more information while iterating. In this example called Growing Cellular Automata, the model is used to generate a single image. Unlike other image-generating algorithms, even if part of the image is erased, it will soon be recovered through iterating. It takes mainly 5 steps to build such a model. Firstly, we need an initial canvas at step 0. In this example, the canvas is an all-zero tensor, except the pixel in the middle of it, where its alpha value is 1. Then we do the iteration. For every step during the iteration, we firstly perform a convolution among every pixels, using some predefined kernels, so that each pixel can extract information from its neighborhood, while having no sense about how the entire image looks like. Secondly, the information extracted is fed into a simple fully connected network. The output should have the same shape as the input, which represents the delta value. The delta will randomly be zeroed based on a predefined probability. The second mask is the aliveness. Only the alive cells and their neighbors can be updated. Our model uses a similar structure as the previous research. However, in order to perform predictions, the values after softmax does not represent RGB, but the probabilities of each class. Note that the softmax function will not be performed on the entire vector. Similar to the previous model, only the first k dimensions represents the probability, so that the softmax are applied to them. Another difference is this legality mask. In this paper, the model is used to predict traffic conditions. The traffic map we used looks like this. We can see that not all the pixels are valid. Some of them are lakes, some of them are parks, and most of them are buildings. These pixels should never be updated, and that's why we have the additional mask. The maps are extracted based on the following locations. The width and the height of a map is 1.6 kilometers. Each map has a size of 80 by 80, so that each pixel represents a square with a side length of 20 meters. We collected 1,126 traffic maps of 10 locations at different times from 6 a.m. to 11 p.m. from Shenzhen, China. The pixels have 4 types of traffic conditions. Green means the best traffic condition, yellow means a little bit of traffic jam, orange is worse, and red is the worst. One cellular automata can only output one target image or target traffic map. In order to do the prediction, it is necessary to input some prior information. Here, we propose a term called pre-explored area, that part of the map is pre-explored. The traffic condition in this region is known. To feed the information into the model, an additional gradient descent step is performed. As a result, the role of ordinary update in the region has become very limited. Here is some test results. We can easily see how the maps are growing. Generally speaking, the model is able to do the original traffic condition prediction. But if the pre-explored area is given like this, the output would not looking good. To some extent, the reason is similar to why we use Harris corner detection to do feature extraction. In the last map, the pattern is missing in the given area, so the model cannot extract effective information from it. In this second example, we tried different initialization policy. The first map is initialized with the same map as the target. The second and the third map is initialized with the same map as the target, but with some missing areas. The fourth and the fifth map is initialized with a totally different map. In this final example, we can see that one model is able to predict different maps. Here we build a simple demo to show how our model works. On the left-hand side, we can see the real-time traffic map, and on the right-hand side is our demo app. So firstly, we can change the map into different locations. And now let's draw some traffic conditions based on the current situation. And now click on the Simulate button and we can see how the model iterates. We can see that our prediction is not too far away from the real situation, especially for the northeast and northwest side of the region. But because we didn't draw too many pixels at the beginning, so there's something wrong with some pixels in the middle of it. And that's all for this video. Thank you very much.